So, from a physical chemistry perspective, these are the standard topics where, what to say, things get switched very easily. So, in this particular case here, when we are going to be considering this week's, what to say, plan for your practice, you got equilibrium, ionic and chemical to an extent, chemical lesser, ionic definitely. You've got thermodynamics and you've got a little bit of chemical bonding. Chemical bonding, maybe not so much, but thermodynamics and equilibrium, both parts are definitely there, right? So, in
Yes.
this here, where are you planning on starting from? I'm guessing chemical equilibrium questions or ionic equilibrium questions or thermodynamics questions. Which one are you looking to start from? Or chemical bonding?
Um, Maybe ionic and chemical equivalence.
Ionic equilibrium, you're planning on starting from there. Okay, all right, okay. So, what are you planning on practicing
Today, sir.
as in package?
Probably first thermodynamics and then
No, no, no. It doesn't matter which
um,
chapter you pick from. You pick something which you are more comfortable from. It's not an issue, but I wanted to know what you're going to be practicing in those. As in, what are you planning on practicing? Have you decided on what you're going to be working on?
um, thermodynamics, sir. I was
Not
just
the chapter.
started doing that.
Where are you picking the questions from?
So the drive, sir.
The
The assignment you gave me, sir.
the assignment I've given you is definitely not at a level where you should start from. Alright, the assignment I've given you is something where you should ideally end at or middle out at, higher middle out at. When you're starting practice questions in a particular chapter, where do you normally start from for other chapters?
F from modules, sir. The
So from the
module they
package
gave.
only, then module package. So they call it, you call it module or they call it module?
We all call it modules.
All of you guys call it module. Okay, so the assignment module is basically, oh, they call it as an assignment module, a separate name, a unique name given for it. Okay, now it makes sense. I'm guessing they call it assignment module, na? What do they call your
Uh,
theory module? They call it theory module or package?
we don't have theory modules.
They have not given you guys any theory books at all this year.
They have, sir, but it is in a different book.
Ah, it is in a
The
different book.
one
I
we
know.
don't.
I know it is in a different book. I'm asking. They have given that also, na? What do they call that?
Yes, sir. Narayana module.
Oh, it is called Narayana module. This is called.
A module. Simple module.
Okay, and this is given only in your campus or in all campuses also?
Probably in all of the campuses.
All campuses, they are giving the same assignment module now.
For high tech division.
Oh, okay, so for all KK campus, they are giving this module
I think so, sir. Yes.
only for his campus.
I think like the high tech division, whatever, like 4, 5 are there. So I think those.
I'm very interested in seeing what is happening because I worked in both those campuses. I mean, my main campus, though, where I worked in your campus only for like not your campus. You not call it your campus. That was a very different campus a long time back. And most of my time I spent in the main competing campus when they were combined. When I worked, they were combined together. They were not independent entities. Chaitanya and Narayana had a combo at that time, and like that was ridiculously different. But anyway, now what I was mentioning was I was working mainly for a long period of time. My last employer in this industry was a dean called Ashok. Ashok sir was the dean who was mainly competing with KK sir actually. So yeah, if this is being given only for high techs division, I'm curious about the jealousy of my previous boss or what my previous boss has done to react to it, because he would not have kept quiet as well. He would have released his own version probably because he has enough, what to say, capability to get it to be released as well. It's not a problem. Very interesting. So how many years has this been happening? Extra special assignment module for you guys?
Don't know, sir. Like since I've joined, they've like given a module.
I'm
So,
asking, is it for your seniors also or only for you kids?
um, no clarity, sir. I don't.
No idea. Okay. All right. Let's get to what I was planning on then. So I was asking mainly to find out where you practice your questions from. So mainly it is the module which you practice your questions from. Okay. So if it is a module which you practice your questions from, go ahead and do the same thing which you have been doing consistently. The assignment I had given you, thermodynamics. Let me just check out what I had put for you. If it was a longer assignment, yeah, they were longer assignments only. They were not short ones. I think these are big ones. Yep, these will have a reasonably large number of questions. But it looks like the assignment I've given you is not too shabby also. I've given mains level questions also in them. Okay, okay. At that time, I had assumed you knew nothing and then proceeded and made the assignment. Okay, huh? Okay, all right, huh? That's why it's relatively decent. Easier plus tougher is also there. You can practice from the assignment itself directly. That will also work. And package ko whenever you have time, do have a not package. You guys call it module. The assignment module whenever you have time, practice that also. You can start from anywhere for thermodynamics. Relatively, it is okay. But the assignment which I have given you is not what to say full. Ideally, once you have completed both or once you have done one of them and skimmed through the other, it should basically be sufficient. Whichever one you wish to finish first, you can finish, and you can skim through the other one for full completion. Ideally, though, if you're skimming through the other one, you should finish doing it within, like, say, 5 to 10 days of this one, of whichever one you are doing. Because, simply speaking, to put it this way, your first round of finishing should be properly fresh in your brain, by which time you are skimming the second round. If it is not fresh, you won't be able to skim properly. You'll have to sit and solve more in that round also. Do you understand how I want you to plan your practice for this over here?
Yes, sir.
Is this how you normally proceed?
Yes, sir. Usually.
Good. And one other thing, ideally speaking, which would be even better, would be old JE questions, a practice of all of them. Because sometimes old JE questions will have some interesting models, which obviously will get repeated in your regular papers also, especially in your module, it will be fully done. So, that aspect is something which anyway will happen, but simultaneously it is simpler to what to say have a quick revision of the old JE questions also. I anyway have started collecting that bunch only because I knew that in your system you are not doing that properly, because you have not mentioned that archive is not a book which you brought along over here, is what you told me, correct?
Yes, sir.
So it is always more simpler to have a book in hand and then sit and practice from there. So I will basically make sure that the archive part of it, I'll take care of that. I will basically try to pick, like, say, 30 questions or so, clean clinical assignment type of thing, like, say, 1.5 hours ish, or maybe maximum 2 hours ish. I'll pick from old JE questions only as much as possible. um, I think the book which I have is up to 2023. I will see if I can get access to some of the newer models of questions also, the last 2 years questions. There should be a good number out of that also, like 500, 600 questions will be there totally for sure. Even if we ignore the repeats, at least 550 questions will be there. So around 550 questions means that's a good lot also. So if I can get my hands on it, I'll have a look at it. By any chance, do you have the old 2024 and 2025 questions with you, chapter wise broken down, JE mains and JE
Mm,
advanced?
no, sir. Not right now.
Okay, but you have a copy of it somewhere available then. Is that correct?
Yes, sir.
Okay. Proper chapter wise?
Yes, sir.
All the questions without skipping any, latest last 2 years.
So like I have like the Arahant book, sir.
Oh, you also have the Arihant book only. Okay. Problem with the Arihant book is I also have the Arihant book up to 2023, but what I notice is they skip some questions here and there. One or two questions in one or two questions in each chapter is at least missing, is what I feel. So yeah, Narayana Chaitanya used to give this, like in our campuses we used to give that after the exam was over. Okay, I will figure it out. If you can get, okay, Arihant book though you have, though that's what you're saying, the actual fat Arihant book you have got.
Yes,
Book
sir.
book book you have.
47 PYQ, sir.
47th, ah. Okay, yeah, mine is 46, so it's 1 year after mine, one edition after mine. So you have till 2024 then in that, correct?
Yes, sir.
Okay, all right. So then you are anyway planning on starting off with ionic equilibrium or one of those places only. So I was planning on basically running through theory of ionic equilibrium now today. So let me start blasting that off. Equilibrium, wherever possible, chemical equilibrium also I'll touch upon it. You want me to touch upon chemical equilibrium theory also first?
Sure, sir.
Okay, all right. Then I'll try to touch up a little bit on chemical equilibrium theory and I'll directly jump on to ionic equilibrium straight away. Okay. Okay. So equilibrium and ionic, no? All right. Now, in thermodynamics, there is actually a part which I have not discussed. I knew what I was doing, so I specifically cut that piece out to discuss it at the end of the equilibrium theory discussion. That part was where thermodynamics connects with equilibrium and how it connects with the next part of chemistry, which is going to be electrochemistry. So, electrochemistry you have not covered in your school as of now, so I'm not going to directly discuss those connections in very much detail, but ideally speaking I'll be looking to touch upon some of those connections towards the end of the discussion there, so that all three of your chapters are properly seamlessly connected. Whenever electrochemistry happens, you can make those connections, the formula connections necessary at that time and the practice connections at that time. Okay, so let's start off with equilibrium now. So the idea is very straightforward. When you're going to be having any reaction, most reactions are going to be never going to full completion. Bulk of the reactions are going to be, what do you say, reversibly happening. So let's take a simple example: A plus B in equilibrium with C plus D. So if they're going to be reversibly happening, the idea is now going to be about what is meant by this particular reversibly happening. What happens if a reaction is happening reversibly? If a reaction is happening reversibly, it means that it is going to be happening both in the forward direction and in the backward direction simultaneously. So you're going to be having backward and forward direction happening at the same conditions. So when we say simultaneously, simultaneously effectively means at the same conditions they should be happening. If they are happening at the same conditions, let's try to analyze what is going to be happening with respect to the speed of each direction over here. So the rate of the forward direction is something which is proportional to concentration of A. In this case here, if I had it as A molecules of A, this will become A power A. If I am going to be having no particular molecule of A present over there, I will be having it as power 1 only. Now let's quickly understand this over here as to why this is going to be. This is called as law of mass action. Now why is this happening over here? This actually comes from something which you should have learnt in a chapter called states of matter under van der Waals actually. Now when we are going to be talking about van der Waals equation over here, that is something which has been technically removed out of your syllabus now. So I will give you a quick brief idea as to why I said no need. I'm not going to explain to you why I said van der Waals though, but I'll give you the derivation of this a little bit over here, the understanding behind it. So if I'm going to be looking at rate of forward direction, in this particular case here, let's take a very simple reaction over here. A simple reaction where you are going to be killing mosquitoes with a bat. Alright. And the game is going to be about finding out when can you kill mosquitoes to a greater extent. Under what experimental conditions can you kill them to a greater extent. So if I'm going to be looking at say killing mosquitoes in a confined space like a cupboard. So let's say I'm going to be having say some item which is going to be somehow or the other storing water in it present in a cupboard. I'm going to be having the cupboard being closed normally. So there's like 1,000 mosquitoes in a small cupboard which is going to be in your house or in some corner of your house. Now that is going to be case 1. In case 2 you're going to be having effectively speaking you're going to be having 1,000 mosquitoes in a cupboard. No need to call it 1,000 mosquitoes in a cupboard. Let's make it 100 mosquitoes in a cupboard there. And in another case, there is 1,000 mosquitoes available in your entire in your entire house. You should be living in a village right now. That means it should be like some kind of nice independent place. So villa type hoga ya chota ghar type hoga. So in that particular villa type thing, definitely there's going to be some land around. There will be enough mosquitoes at night time if there is water, if there is farms nearby. So the idea here is you're going to be looking at say 1,000 mosquitoes in your full apartment and 100 mosquitoes in a cupboard. The question now is when can you kill mosquitoes faster? That is of course going to be mainly dependent on the concentration of the mosquitoes. So if I'm going to be having say or if you're going to be having the mosquitoes in a much more denser concentration, then you can basically kill them faster. So the speed at which you can kill mosquitoes depends on the concentration of the mosquitoes in a particular location there. Simultaneously, why does it depend on the concentration of a mosquito? You can think of it as this is going to be the speed of the reaction. It is going to be dependent on picking one mosquito which is going to be killed at a particular unit interval of time. So if I'm going to be breaking down all the mosquitoes that are going to get killed in terms of a time axis, right, if I'm putting a time axis over here, then yes, you'll have multiple mosquitoes getting killed at every instant if you are lucky. And if you are going to be having a bat, again in this case here the second condition which I was going to plan on discussing was if you have one bat in one case and if you have two bats in one case, in which case can you kill the mosquitoes faster. Of course when you're going to be having more number of bats, you're going to be able to use both your hands in a more meaningful manner. So if you have found a nice location where the density of mosquitoes is very high, you can increase your speed tremendously by simply using both bats at the same time. So density of mosquitoes is going to be depending definitely over here and it is directly proportional to it. That is speed of killing mosquitoes will directly be dependent on that. And simultaneously it is also dependent on how many bats you are having simultaneously and how efficiently you can kill the mosquitoes as well. So it depends on the concentration of the bats on your person as well. So it doesn't matter if you are going to be having one extra bat in some corner of the room and only nothing in your hand right now. You're going to be slower. So the idea here is it is absolutely going to depend on both the factors here. So you can think of factor A as say the mosquitoes here and factor B as the bats, or factor B as the mosquitoes, factor A as the bats. It doesn't make a difference. So you're going to be having rate of killing mosquitoes or rate of doing a process is going to be depending on picking the molecules involved in that process for sure, which means it is going to be involving probability of finding each and every one of those molecules. In this particular case here, I'm going to be equating the mosquito and the bat to the molecule over here. So the chance of having a kill occurring is when you're going to be having a mosquito bat and the mosquito in connection. Only when they are in connection do you end up having a reaction which is going to be the killing of the mosquito in this process over here. So the idea here is you're going to be having a reaction here depending on the chance of the probability of finding both of those particular items which are supposed to be reacting at the same space at the same time. That is the key point over here. So we are going to be localizing these two objects in space and time. So it depends on probability of finding each and every one of those particles. So if you're going to be having say A moles of A, that means in that reaction there, at a time you're going to be having A molecules of A being present at the same space at the same time. That is why if you're going to be having any particular rate of law of mass action considered, it is going to be something which depends on finding A molecules of A now, not just one molecule of A, but A molecules of A at the same space at the same time. Now, obviously, in this particular case, the rate is going to be only proportional to, we can't say it is equal to. Because ultimately, if you are going to be in a much more irritated mood, let's say you have been trying to sleep for like half an hour, but the mosquitoes have been irritating you with the sound. Yes, there is no mosquito in your room. You are able to manage, but it is not completely soundproofed. And the white noise of buzzing mosquitoes is not comfortable to you. Normally, it is very good to sleep. But if it is right next to your ears, it is very, very irritating. So yeah, let's say you are now getting irritated. You want to go kill some mosquitoes and then come back to sleep because you have not been able to get sleep properly. In that case, you are more motivated to go kill the mosquitoes. You will be taking more energy out of it. You will be doing a better job at killing them. Whereas if it is going to be the other scenario there, if you are basically like just woken up, yeah, the mosquitoes are irritating, but you have had a good sleep. Now you want to lie down in bed for longer. You don't care about the mosquitoes so much right now. You want to lie down in bed for longer and relax over there. So you are not going to be that effective at killing the mosquitoes at this point over here. So the rate at which you are going to be killing, you can't say it is only dependent on that. It is also dependent on your mood over here to perform the reaction. So effectively speaking, that is like the temperature aspect or the rate constant aspect which comes into play here. So we can say that rate of a forward direction reaction or any reaction can be written as some constant. In this case, because it is going to be rate constant, we are going to be having it as constant with respect to speed here. So I'm going to call it as rate constant. That rate constant is depicted by K over here. And because it's a forward direction which I'm considering, I'm going to put it as Kf in this particular case here. Multiplied by concentration of A power A multiplied by concentration of B power B. So in this particular case here, if I was having B molecules of B also involved, we would have it in this fashion like this. Kf into A power A into B power B. So this is called as law of mass action. Now this same nonsense is going to be applicable for the backward direction also. In that sense, we will be having rate of backward direction, which is going to be simply written as rate of B is going to be equal to Kb multiplied by C moles of C into D moles of D. Of course, in this particular case here, what kind of equation am I assuming? I am assuming A moles of A plus B moles of B in equilibrium with C moles of C plus D moles of D. So this is the equation I am going to be considering as the parent equation over here. Now in this equation here, forward and backward are both happening at the same time at different speeds because they are dependent on different reactant molecules with respect to each of them. For the backward direction, the reactants are the products. For the forward direction, the reactants are the reactants. So in this case here, what happens is, if I'm going to be having both of them being different, what will happen in this process here? We can try to look at the process which will be happening over here. If let us say at a particular condition, rate of forward direction is being greater than the rate of backward direction, what will happen in that particular case is more of the forward direction of the reaction will be happening at that instant and lesser amount of the backward direction of the reaction will be happening, which means over time from this point of time. So let's call this at time t1. So at time t1, we are going to be having more forward than backward happening. More forward direction than backward direction. So in this particular case here, what happens is when you're having more forward direction than backward direction, you're going to be having concentration of reactants decreases very fast because they are being consumed in greater quantity. So they are going to be consumed at a much greater speed over here. So if the concentration of reactants gets consumed very fast, this also means rate of forward direction decreases over time. So as I am going to be having the forward direction happening to a greater extent, I will have rate of the forward direction decreasing faster over time. This means more products get produced. More products get produced. Which means you're going to be having products concentration increasing over time in this particular case here. So if I'm going to be having products concentration increasing over time, this basically means I'm going to be having rate of the backward direction increasing over time. So I will have rate of forward direction decreasing over time, but I will be having rate of backward direction increasing over time. So effectively this is going to be increasing, while this is going to be, damn, I made a mistake here, sorry. Forward direction is decreasing, backward direction is increasing. So what happens in this particular case is this will decrease, meaning it will come down, and you will have rate of forward direction initially being above rate of backward direction, but this is decreasing over time, this is increasing over time. Ultimately you will have a point at which they both become equal. So at some point of time, which is going to be say T equilibrium, we will be having rate of the forward direction of a reaction becoming equal to rate of the backward direction of the reaction. What happens at this point in time? At this point in time, you're going to be having concentration of reactants and products not changing anymore. So this is going to be called as your equilibrium point. Okay, so how do we understand this equilibrium? How do we measure this equilibrium? Basically the idea here is an equilibrium is going to mean you're going to be having concentration of anything which is involved in the reaction, reactants or products, should not change over time. That is the idea over here. So if I'm going to be saying it's going to be not changing over time, that means d of concentration of reactants by dt or d of concentration of products by dt. Both of these should be equal to 0. This is the idea over here at equilibrium, or at time equal to equilibrium, or you can say or after time equal to equilibrium. Now how do we mathematically represent this idea over here? Mathematically we are going to be representing this idea very simply as rate of forward direction, which is going to be kf into concentration of A power A into B power B, should be equal to kb into concentration of C power C into concentration of D power D. So from here we will be having, we are going to be taking the constants to one side and the variables to the other side. So kf by kb works out to be equal to concentration of C power C into D power D divided by A power A into B power B. This part over here we are going to be now combining and calling it as a new constant, which is called as equilibrium constant, K equilibrium. So this K equilibrium is going to be nothing but what is referred to as the equilibrium constant, and this particular equilibrium constant is nothing but rate constant of forward by rate constant of backward. So these two guys, the rate constant of forward and backward here, they actually are going to be factors from chemical kinetics. Where from specifically in chemical kinetics? From Arrhenius equation. Have you completed chemical kinetics so far? In physical chemistry? Schoolmen? It's completed now. You familiar with Arrhenius equation or not, Arun? That's basically what I'm asking.
Yes.
Okay, alright. So this is basically going to be coming from chemical kinetics from Arrhenius equation part over there. Alright, so in this particular case here, you're going to be having this as your equilibrium constant. Now let's try to understand this equilibrium constant a little bit more and see what is the reason or what are the ways to use it over here and what are the properties for this over here a little bit more carefully. So when you're going to be having this equilibrium constant here, you're going to be having this equilibrium constant being some form of activity or some form of probability of finding a molecule of C, power C, multiplied by probability of finding a molecule of D, power D, divided by probability of finding a molecule of A, power A, divided by probability of finding a molecule of B, power B. That is basically what this is. That probability of finding each of these molecules here is going to be something which is going to be depending on a concentration term, which doesn't change in this particular case at a given temperature, because K equilibrium is going to be a constant at a given temperature, constant at given temperature for given reaction. So when you're going to be having this equilibrium constant over here considered over here, this is going to be, of course, you're going to be using concentration terms which do not change over time here randomly. So these concentration terms which are going to be used over here, they have to be concentration terms. So for instance, Kc, where you're going to be writing it in terms of concentration, molarity. This is going to be something which is going to be an equilibrium constant. It works as an equilibrium constant perfectly well. Similarly, if I'm going to be writing partial pressures, this is going to be again another concentration term. In this case, we are going to be using partial pressures. This is also going to be an equilibrium constant, in the sense this also works like an equilibrium constant. Where do we usually use each of these over here? Kc is going to be used when you are going to be having solutions or liquids generally taken into consideration. When do we use Kp? Kp is going to be used when you are going to be using for gases usually. Alright, so depending on which one you are going to be having as a greater component at play there, you're going to be having that particular equilibrium constant usually chosen. But for gases, you can of course definitely have Kc also. Kc is also applicable for gases. It doesn't mean Kc for Kc, for gases you are not going to be having Kc being applicable. So for gases, Kc also works or also can be used. But usually when they are mentioning equilibrium constant and they forget to say something about it, you can generally be taken, you are perfectly fine to take it as Kp when it comes to gases, and you are perfectly fine with taking it as Kc when it comes to solutions. But just to play with you, once in a while they will give Kc for gases also. So be ready for that. We are in a competitive system. They are going to be making sure they play with you in every way possible. So this is going to be the idea in this particular case here. So when you're going to be having equilibrium constant, let's quickly understand why these two are meant to be considered as equilibrium constants. Molarity is of course going to be a given. This is the standard one, which is obvious. Now for gases, why is partial pressure acceptable? Because you can effectively write for an ideal gas. This is of course going to be meant for an ideal gas, not for some random gas. For random gases, of course, Kp is going to be applicable. Real gases also it is applicable. But there will be other correcting factors involved over there. So let's look for an ideal gas first. For an ideal gas, what is going to be happening over here is you're going to be having, of course, PV is equal to nRT. Or actually speaking, for even a real gas, some form of this equation is applicable. Some extra constants will be there, some extra terms will be there. It doesn't matter. So basically P can be written as N by V into R into T. So effectively speaking, this N by V becomes your molarity. So this is going to be concentration, which means we can definitely use partial pressure. This is of course going to be partial pressure. So partial pressure and concentration for a gas are related in this particular equation over here, as you can clearly see here. Partial pressure is equal to concentration into R into T. If you're going to be having certain specific conditions with a real gas, they might give you some extra variable like say compressibility factor, or effectively it is still going to be concentration into RT with a few extra powers for temperature or concentration playing a role. So you're going to be having partial pressure always being this way. Ideal gas ke liye it is going to be directly proportional. Alright, so for any ideal gas here, we'll be having partial pressure of gas being equal to concentration into R into T. Okay, so this is going to be the case over here. So you can effectively convert your Kc and Kp into each other depending on how you wish to convert your concentration terms over there. For instance, let's look at how to do this conversion over here quickly. So if I'm going to be having say Kp for a gas considered. Now in this case here, Kp for an equilibrium is what I'm considering actually. But of course, if I'm saying for a gas over here, what do I mean here? I mean that all the components are gases. So let's say I'm going to be having a proper homogeneous equilibrium. Homogeneous equilibrium, what does that mean? It basically means that all the pieces which are present in the equilibrium are in the same physical state where they are interacting with each other in a same uniform manner. The uniformity of interaction matters over here. So in this particular case, I'm going to be considering a homogeneous gas equilibria to basically look at the situation here. So let's make it the same type as earlier. A moles of A gas plus B moles of B gas is in equilibrium with C moles of C gas plus D moles of D gas. In this case here, we can of course have a Kc associated with it, or we can have a Kp associated with it. What we are trying to do now is to understand the relationship between the Kc and the Kp in this particular case here. So if I'm going to be considering a Kp for an equilibrium here, we can of course write it as partial pressure of, in this particular case, products by reactants. So Pc to the power of C multiplied by Pd to the power of D divided by, I'm of course going to be having P of A to the power of A multiplied by P of B to the power of B. So effectively manipulating this slightly, each of the partial pressures can be written as partial pressure of gas is going to be nothing but concentration into R into T, as you can see over here. Straight away play around with that. So we end up having partial pressure is concentration into RT. So this can be written as concentration of C power C into RT whole to the power of C. Of course, you're going to be also having concentration of D power D over here, but you're going to be having the D over here also having an RT power D. Since it's multiplied, we can now add it over here directly. Divided by, we are going to be having in this particular case, concentration of A power A multiplied by, we will of course be having RT to the power of A. And we are going to be having in this particular case, of course, the last term is going to be concentration of B power B, which is of course going to be simultaneously having a plus B also associated in the denominator over here, which means we can effectively write it as, we can combine all of these products and these terms over here, specifically speaking. I should not have combined it so nicely. So I'm going to be combining all of these terms together, while I'm going to be leaving the RT terms out individually. So we're going to be having it as effectively concentration of C power C into D power D by concentration of A power A into B power B, multiplied by, of course, you're going to be having RT whole to the power of C plus D minus A minus B. So we're going to be having in this particular case here, this C plus D minus A minus B, we're going to be putting that out as effectively delta N in this case here. Of course, delta Ng, because only gases should be counted over here. And of course, this entire fat term is going to be a nice Kc of the particular equilibrium. So you can write Kp of the equilibrium is going to be equal to Kc of the equilibrium multiplied by RT whole to the power of delta Ng. This is going to be the equation which you are going to be arriving at in this particular case here. So when you're going to be having this as the equation, this is going to be directly giving you a link between the Kp expression for equilibrium and the Kc expression for equilibrium. Both those equilibrium expressions can be considered as an equilibrium constant. So what does it mean to basically have that expression here? All of these expressions which we are understanding or which we are looking at over here, how do we use them? What is the idea behind how to use them? How to use them, and the way to use them goes with respect to defining a new term called as reaction quotient. There will be a couple of new terms which we are going to be discussing over here. So one new term is going to be what is called as a reaction quotient. What is the idea behind this reaction quotient? See, your equation or the reaction which we are going to be considering, A plus B in equilibrium with C plus D. This is something where you're going to be having reactants and products reacting simultaneously with each other. So when you're going to be having this reaction happening here, at starting time t1, in this case where we started off, we tried understanding if rate of forward direction was going to be greater than rate of backward direction. We started off with that case and tried to analyze what is happening there. So we took a time t1 over there when we mixed them at random composition. We didn't know what the exact scenario was. We mixed them at a random composition and then they slowly reached equilibrium. So at some time start t1 over here, when the reaction is just being mixed together, there will be no equilibrium. What happens is, slowly, regardless of what the composition of the mixture is going to be, if rate of forward direction is greater than rate of backward direction, we discuss the case. If rate of backward is greater than rate of forward, what will happen? More of reactants are being produced, so rate of forward direction is increasing, but more of products is being consumed, so rate of backward direction is decreasing. So if rate of backward is higher than rate of forward, slowly the products are going to get consumed and the rate of backward is now going to be decreasing. And simultaneously reactants are going to be produced, so rate of forward keeps increasing. Ultimately they both reach an equality, which is going to be your equilibrium here. So regardless of where you start a particular reaction which is reversible, whichever point of concentrations which you end up starting at, let's call that as starting T1. At that point there may be equilibrium, may not be equilibrium. We are not looking at it necessarily at equilibrium over there. No equilibrium for sure, or rather no equilibrium which we can't confirm equilibrium. So in this case here, this reaches equilibrium, or we can say it moves toward equilibrium. So as it moves toward equilibrium, what is going to be happening in this particular case here? You're going to be having this particular reaction here. As it moves toward equilibrium, it will finally reach a time where it is at equilibrium. So if it is going to be at equilibrium, there are going to be the conditions which we can calculate out perfectly comfortably. Why? Because if I am a scientist who is observing a reaction mixture, something is continuously changing, then what is the point of me sticking my conditions over there and finding what the current concentrations are? It is going to be changing over time anyway. So finding that out is going to be taking me time. By the time I come back, my observation is different now. So I have gotten information about what it was at that time when I did the measurement. And that also slowed down during my process of measurement also. Because remember, when I take a sample to go measure, it is going to be changing inside that sample which I am taking also, because that sample is going to be a sample of the original. So the original and the sample are both going to be changing. So it is a complicated pain over there when the concentrations are changing. So scientists, what they like to do, of course, is they wait for the stupid thing to stop reacting. And then they stick their sample over there, they take it out, then they analyze it and find out what is the case there. So at equilibrium, at a time where it has reached equilibrium, we would have calculated the K equilibrium for the reaction. It can be either a Kp if it is going to be meant for gases only predominantly, or if it is going to be considering something which is going to be having liquids and solutions only. Solids are also there, solids I don't care. So if I am going to be having liquids, solutions, no gases, or very few, and maybe solids present. In these cases here, we will usually be considering, or we will be given Kc. Why? I will explain later. This is where your electrochemistry comes into play here. So in these cases, you're going to be having Kc being the most common thing given. But that is going to be only the case if you're going to be considering in this chapter over here. Alright. In equilibrium, it is going to be like that. Whereas from electrochemistry point of view, I'm mentioning the general way in which this is going to be given in electrochemistry. In electrochemistry, it is going to be a mix. The solutions and liquids will be equilibrium with respect to C. And when it comes to the gases though, we will end up having partial pressure of the gas being the conditionality over there. I'll explain what I mean about this and how this is to be written in that chapter or in the connection between these two chapters at the end of this chapter, where we connect it with thermodynamics also. Now in the case of only gases or mainly gases, we will have Kp being used predominantly. Okay, we have already discussed how to connect the Kp and the Kc as necessary in the previous part over there. So what is going to be happening is, now when we are going to be looking at this no equilibrium or the part trying to reach towards equilibrium or moving towards equilibrium, if we are looking to analyze that and understand that particular time period more efficiently, that is, I want to understand this time period as to what is happening for the reaction, how to analyze that if we are able to do the measurements faster and faster. We ended up or rather the scientists ended up deciding on using a term called as reaction quotient. What is this reaction quotient going to be doing? It is going to be nothing but same expression as K equilibrium, formula wise, but at any time t. That is the idea over here. But at any time t. Whereas K equilibrium, Kp or Kc or whatever you're going to be defining in that fashion there, that is something which you have applicably done only at equilibrium condition over there. So what is this reaction quotient Q? The reaction quotient Q is a tool which is going to be very, very helpful in understanding whether a reaction is technically moving. I mean, what is the mathematical idea as to how it is moving towards equilibrium? You will be able to get that connection very easily. So what is reaction quotient? It is going to be same expression as equilibrium constant, same expression as K equilibrium, but at all time t, but at any time t. That is the idea over here. So we will be having K equilibrium being the same as only at equilibrium. When I say only at or after, because when something reaches equilibrium, it always tries to go back to the same equilibrium. So even if you disturb it slightly, so only at or after T equilibrium has been reached, you're going to be having K equilibrium being calculated here. Now let's see how this Q equilibrium or Q, no, see, it should not be called as Q equilibrium. Why I ended up getting that in my tongue is because usually kids make a mistake when they think of Q as equilibrium constant also. It is not an equilibrium constant. What are the equilibrium constants? Only Kp and Kc are equilibrium constants. We will talk about the other variable, other tool also, mathematical tool also we'll be using in this chapter quite often in the next part over there. So K equilibrium, only at or after T equilibrium is this supposed to be considered as K equilibrium. So Q is what we call it at all other times here. So let's consider the different ways in which the Q can be considered over here. So if I am going to be having Q being equal to K equilibrium, this is the obviously straightforward most easy condition. This means the reaction is already at equilibrium. We don't need to think about it more than that. It is already at equilibrium. Concentrations of reactants and products are not changing. That is the idea over here. So already at equilibrium, meaning this is going to be your time at or after T equilibrium. So no problems there. We don't need to care about what is happening. If I am going to be having Q being greater than K equilibrium, what does that tell me? The expression here is going to be nothing but products by reactants. I don't care what they are in terms of products. I don't care what they are in terms of reactants. But it is effectively products by reactants. So if it is supposed to be products by reactants over here, that is now going to be greater than expected. So what should happen over here implies it moves towards equilibrium. So Q decreases and moves towards K equilibrium. That is what must happen over here. Because there is no other option here. It can't go up and randomly come back to K equilibrium. The idea here is if a reaction is starting at a particular point in time, is it going to go more away from equilibrium and then start coming back to equilibrium, or it immediately starts moving towards equilibrium? It immediately starts moving towards equilibrium. That is the key point to understand over here. So if I am going to be considering a reaction, this is going to be something where it connects with thermodynamics. So I want you to pay attention to the words I am using here. If any reaction is not at equilibrium, it immediately starts moving towards equilibrium, or we can say it immediately starts only moving, because it is not just moving but it is only moving towards equilibrium. It doesn't randomly go away from equilibrium and then come back there. Alright, so it immediately starts only moving towards equilibrium when left alone. That is another key point to basically talk about here. What does when left alone indicate here? When surroundings is not poking it. So this when left alone part over here indicates no interference from surroundings. This is the idea in this particular case over here. So when you're going to be considering an equilibrium, this is basically how it works over here. So if I had Q greater than K equilibrium, Q immediately decreases and moves towards K equilibrium. That is the key point over here. So in this case, if Q is decreasing, that means this entire thing has to decrease. If this entire thing has to decrease, that means product should decrease. That is one way of getting it done, or reactance should increase, or both should happen simultaneously. So if I am going to be having the Q decreasing and it is moving more towards equilibrium, effectively what is going to be happening is both will start happening. So in this particular case, what can we think of this as? Product's concentration decreases over time, and we are of course going to be having reactance concentration increasing over time. That is going to be the case in this scenario over here consistently. So if I'm going to be having this as the case in this scenario over here consistently, what will happen? Effectively, both of these will combine to basically mean Q is going to be decreasing over time, and we are going to be having the Q effectively reaching K and becoming a stage where it is at equilibrium properly, comfortably. Opposite also works out. If I am going to be having Q less than K equilibrium, in this particular case here, we should be having the products increasing because you want it to increase over here. So in this particular case here, Q increases over time to become equal to K equilibrium. That is the idea over here. So let's study that over here in more detail over here. So when you're going to be having Q being less than K equilibrium, this means we are going to be having products by reactance needs to increase, has to increase over here. So if it has to increase over here, what is the easiest way of making them increase? This fellow increases, and we are going to be having the denominator bugger over here decreasing. So if you want the overall mathematical function to increase, easiest way is to have products increasing and reactants decreasing over here. So this basically means we are going to be having products increasing and reactants decreasing at the same time. This of course is going to be indicating what is called as forward direction of reaction, because in the forward direction, if more forward direction is happening, we are going to be having more of the products being produced and the reactants being consumed in the process over there. So this means effectively more forward direction happens or is happening. At what condition? At this condition where I am going to be having Q being less than K equilibrium. Now this is going to be the case in this scenario here. Of course, the other side also holds good over here, in the sense the same logic applies in the opposite direction also. What is the opposite direction? The one which we discussed in the previous page over here, where we are going to be having, if Q is going to be lesser, then how does it move towards equilibrium over here? So if Q is going to be lesser than K, Q is greater than K now, in this case it was Q greater than K, So Q greater than K, Q lesser than K is the one which I have just put up over here, that's why I had to check up once. So Q greater than K equilibrium here, if I am going to be considering that case. What happens in that particular case? Q is greater means products are already greater. So products now decreases, reactants now ends up increasing. So we'll end up having in this case here, products will decrease over time and reactants are going to be increasing over time. This of course basically means this is going to be nothing but backward direction is technically happening over here. So backward direction of reaction. That is basically what this means over here. This also can translate into more backward direction is happening instead of forward direction at that particular instant in time. It doesn't mean forward is not happening. It means it is happening to such a small extent over here that the backward direction is happening to a much greater extent, and if you are measuring something, it looks like only backward direction is happening. Looks like. Internally both will be happening though. Okay, so this is basically the idea when it comes to how to use reaction quotient, how to play with it, what are the mathematical ways of using this mathematical tool. So as I said, this is a mathematical tool, it has nothing else to do with things. Now next up, When you're going to be looking at the next part over here, you're going to be having another mathematical tool here, which is going to be referred to as kx. What is this kx over here? The kx over here is going to be the expression for k equilibrium using mole fractions. Now, why do we use this over here? What do I mean by this? We can effectively say that this kx over here is going to be nothing but mole fraction of, say, I'm assuming the same equation, a plus b, a moles of a plus b moles of b giving c moles of c plus d moles of d. So I'll just put that guy over here. So a moles of a plus b moles of b in equilibrium with c moles of c plus d moles of d. This is the equation to consider over here. So in this case, we're going to be having mole fraction of c power c multiplied by mole fraction of d power d divided by mole fraction of a power a multiplied by mole fraction of b power b. This is what we have over here. So this is going to be referred to as kx over here. This kx is not an equilibrium constant. Okay, so this kx over here is not an equilibrium constant, meaning this can change at given temperature. Why is it something which can change at given temperature? Because it depends on two factors over here. It depends on pressure also. Depends on total pressure of system. Also, it depends on temperature, yes, but it also depends on total pressure of system. Because it depends on total pressure of system, it is not something which can be considered as an equilibrium constant effectively. So let's try to understand what is the link between the Kp and this nonsense over here. So very simply put, when you're going to be considering the link between these two over here, it is going to be fairly straightforward. You're going to be, now in the previous case when we looked at link between Kp and the Kc, we linked them up using concentration. Here we're going to be linking them up using, what to say, other type of scenario here, another equation basically. Dalton's law of partial pressures mainly. So partial pressure of a particular gas like say C can be written as mole fraction of gas C into, we are going to be having in this particular case here, P total. So each of these gases here, we can write it as partial pressure of gas D is going to be mole fraction of gas D into P total, and so on and so forth over here. If I can write it like this, what do we get mole fraction of gas C effectively working out as? Mole fraction of gas C is going to be nothing but partial pressure of gas C divided by P total. That is what we are getting over here. So we're going to be having it as partial pressure of gas C divided by P total in this particular case here. Meaning we can write mole fraction of gas A is also going to be something where it can be written as partial pressure of gas A divided by P total. Effectively, the P total becomes equivalent to 1 in the sense, if I am going to be writing it like this, mole fraction of gas A is mole fraction of A by 1. So this is going to be corresponding to P of A, and the 1 effectively corresponds to the P total part over here. That is the simple idea over here. So if I am going to be putting it in that fashion over here, let's say I am going to be implementing it on this side, we'll now be having this expression working out as Kx being equal to, we'll be applying each of those over here. We'll of course be having each of these terms over here changed by the partial pressure terms over here, meaning it will become partial pressure of C power C multiplied by partial pressure of D power D divided by partial pressure of A power A multiplied by partial pressure of B power B. But we are going to be in each of those cases having it divided by P total also, meaning we are going to be having for the numerator part, we will have divided by P total to the power of, in this case, numerator will have a C plus D present in the denominator part over here. And the denominator will effectively end up sending it into the numerator over here. So we'll end up having this removed out over here also. So we'll now have it as P total over here to the power of A plus B in the numerator over here. So let me re-put it over here in a fresh page over here. We end up having Kx being equal to Kp multiplied by P total to the power of a plus b minus c minus d. So if I'm going to be having it in this fashion here, if I take it to the other side, we end up having kp being equal to kx multiplied by, in this case, p total. I just need to multiply it by a minus 1 over here, meaning it becomes c plus d minus a minus b, which of course can be written as kx into p total to the power of delta ng in this particular case here. This is effectively going to be the connection over here between kp and kx over here. And because it is going to be depending on p total, we are not going to be having kx being an equilibrium constant. So as kx depends on p total, what is p total? P total is p external. That is the basic problem over here. So as kx depends on p total, what is p total going to be? P total is usually going to be p external. At what condition? At equilibrium between surroundings and system. What are we now studying? We are now going deeper into the equilibrium, and we are trying to see the equilibrium of system within itself. System is going to be something which we are studying, and inside the system also there is a much more dynamic equilibrium, which is what we are trying to study now. But in reality, in thermodynamics, what have we studied? In thermodynamics, we have studied that you are going to be having the system also maintaining an equilibrium with the surroundings. How does it maintain an equilibrium with the surroundings? By looking from p external perspective over there. As p external ends up becoming equal to p total, or of a particular, becomes equal to p internal overall, automatically that means system and surroundings are in equilibrium, as long as we as system don't go poke the surroundings any further. So this is going to be the condition over here. As kx depends on p total is going to be nothing but the same as p external, and that p external is going to be nothing but something which we can be sure is going to be a constant, and this is going to be the case at the equilibrium between surroundings and system. Okay, now, so kp is going to be equal to kx into p total whole to the power of delta ng. Wonderful. So we've got this as the next connection over here. So how do we use this? We use this again in questions. In certain questions, they might tell you that this reaction mixture is present at an equilibrium. They might give you temperature. They might give you certain other conditions. In questions where they give you P total of the reaction mixture, this is going to be the easiest method to approach. In questions where they don't give you, depending on what variables they are giving you, we have done enough connections of mathematics here to basically play around with and get your solution done. One more type of question where they can give you equilibrium conditionality in a slightly more unique way. So what are we studying now? We have got equilibrium. We are now looking at how are the different ways we can calculate the various mathematical functions and variables, state variables associated with an equilibrium. What are the state variables associated with an equilibrium? You're going to be having the different concentrations of the different substances, and the equilibrium constant, the temperature and the pressure at which you are measuring all of these things. So these are your various state variables associated with an equilibrium, and what are the mathematical functions connecting those equilibrium pieces together. Okay. One minute. So the next thing we're going to be looking at is two large scale things. What happens when you're going to be having heterogeneous equilibrium, and how to understand how surroundings interacts with equilibrium, and one more thing, one model of question which is very commonly seen in this chapter, and of course one definition as well. The definition we are going to be considering and learning more about is called as alpha, or degree of dissociation. Now when we are going to be talking about degree of dissociation over here, what is the idea over here? If I was going to be having, say, some A moles which is going to be giving me some B plus C. Okay, it's going to break into some B plus C. If I want to understand how this reaction is actually mathematically moving forward, let's start off with, say, at time t1, we are going to be starting off with some concentration of C, which is going to be the amount of reactant A. Let's say we are having nothing of B and C available at that time t. At equilibrium, we will have concentrations changing over here. So when the concentrations are changing here, how are these basically going to be playing out over here? We will end up having to basically understand that yes, some amount of the reaction has happened. So we are going to be having some amount of A consumed over here. So let's say C minus X. If you're going to be having stoichiometric coefficients being 1, 1 and 1, let's change them slightly, 1, 1 and 2. If they are going to be having stoichiometric coefficients 1, 1 and 2, we can say X moles or X amount of A has been consumed over here. So if one amount of A produces only one amount of C, we can see that the amount of C which should have been produced should have been X as well. But one amount of A is producing two amounts of B over here. Meaning for X amounts of A consumed, we'll end up having 2X amounts of B produced over here. So this is basically how the reaction should work out at whatever time T equal to equilibrium. Now the issue here is this is going to be something which is going to be, of course, depending on what is going, the X over here depends on C, right? So X depends on C also. So it is not something which is going to be something which we can think of as a larger scale mathematical function which can be used over here. X is a variable, that's all. So what scientists now decided was, if everybody has to use a standardization, easiest way to standardize this is start with 1. So if I'm going to be looking at alpha, alpha is defined as amount of substance reacted if we started with 1 mole at the beginning. Now you will start realizing this very often, mainly because you will start seeing this very often, especially in the next chapter, electrochemistry, which is the continuation of this flow, so to say. Why you're going to be seeing this very often is because ultimately scientists needed to accept that we will all do standard shit. One dude over here will do that, one dude over here will do this, one dude over here will do that, one more fellow will do something else. None of that shit is working. Why? Because they sat and discussed during the Renaissance era, when the great, invention of science basically happened in Europe. When Europe again came back into the light, as they call it, and went away from the dark ages. What happened was basically people who used to do things, who used to have a lot of time, who had a lot of money, who had a lot of energy on their hands, who knew a lot of shit, when they basically ended up trying to experiment with things and find more about the real world. All of this was for their prestige, obviously. So what happened was they used to effectively find out something new, and that something new which they had found out, they needed to confirm. Is this working everywhere? Because if it works everywhere, they can use it to make money. Ultimately, their goal is to make more money, have more, wealthy things, be having more free time to conduct more experiments. That is their goal. So that they can have more new data, they can go basically talk about it to their friends, show off to their friends, dekho what I am doing, how I am wasting time, how professionally I am wasting time, and how much time I am basically investing technically to make more money for myself. So how they used to do it was, they used to have like group discussions, group meetings. They used to meet up for lunch, they used to meet up for dinner, they used to meet up for drinks, and they used to discuss all this kind of nonsense. So when they used to do this, they realized that they needed their information confirmed by their friends in other places. Instead of them going and doing that thing, they would prefer that their friends confirm it for them. So for that sake of confirmation, they needed a set of standardizations done, so that the data collected over here can be confirmed over there once. Always, measure but confirm at least once or twice. So in this case here, in almost all the scenarios, they will define something with 1 mole being at the beginning. Why? Because 1 mole or 1 standard amount is a very easy thing to basically confirm and measure across different scientists. Every scientist knows how to measure that 1 particular mole of any random substance. They can take that properly, they can measure it in terms of grams, in terms of whatever volume you're putting it in. All of those measurements can be done perfectly comfortably. Same goes for partial pressure. So when it comes to standardization with respect to concentration, we will of course be using 1 mole per liter. When it comes to standardization for any gas, we will of course be using partial pressure of gas, and we'll be defining it as 1 atmosphere usually. That is Just make sure that the entire container is filled up with that and it is at equilibrium with your outside automatically. That is going to be 1 atmosphere. Easiest conditions is all that we care about. That is all they did also. So they defined this alpha with respect to 1 mole being at the starting here. So alpha is going to be amount dissociated if we start with 1 mole. Meaning we are going to be having, in this particular case, the same expression we can write it as, let's forget about the A moles of A over there, we'll just mention it as 1 mole of A is going to be giving me 1 mole of B plus 1 mole of C, or 2 moles of B plus 1 mole of C. So if I started off with 1, this was 0, this was 0, means this will be now written as 1 minus alpha at equilibrium, and this will end up becoming 2 alpha, this will become alpha. So in all of these cases over here, you will be given some conditionality over here. Either the alpha will be given or the equilibrium constant will be given. How can I write my equilibrium constant? Equilibrium constant is of course going to be B squared, which is going to be 2 alpha whole squared multiplied by alpha divided by 1 minus alpha. This is basically how you write your K equilibrium. So if you are able to calculate the K equilibrium, you can now get your alpha also out. Or you can now check how they are related to each other if you know the alpha here. So if I am going to be having a random equation happening, alright, where I am going to be having, say, instead of A moles of A, let's say I am having, instead of 1 mole of A, I am having, say, A moles of A plus B moles of B in equilibrium with C moles of C plus D moles of D. If this is the case over here, what I'm going to be having is, let's say I'm having some random moles over here of A, C1 being present over here. Okay, let's say I'm going to be, let's not look at the B moles of B, that complicates things a little bit more. So let's take it as A moles of A is going to be in equilibrium with each of these over here. Okay, so A moles of A is in equilibrium with C moles of C plus D moles of D. So if I'm going to be having it like this, instead of the D here, I'll change it into B over here. That will be more simpler as well. Okay, so if I have it like this, so in this case here, we will be having, let's say, C as the starting amount of A. If C is the amount of A available at starting, then we are going to be having, let's take it as a simpler case. Instead of A moles of A here, we'll take it as 1 mole of A first, then we'll go for C moles, A moles of A there. So if I have it like this, C is my starting concentration here. Now we will have C into 1 minus alpha being the amount which is going to be technically considered here. In the sense, we are taken it as C minus X over here, correct? This X over here, we are now going to be simply considering it as nothing but C times alpha. That is the idea over here. This X which has been consumed over here is nothing but C times alpha in this particular scenario over here. So you're going to be having it as C into 1 minus alpha over here. These two would have been 0 and 0 in the beginning. This will become, of course, well, you're going to be having, again I have to change this nonsense again because I'm having same variable over here. I'll not care about the C here. I'm only going to consider the B here. Other things, it doesn't matter anyway. So if I'm going to be having A giving me B moles of B here, I'm going to be having A changing from C into C, from C it will become C into 1 minus alpha, where it is actually going to be C minus C alpha actually, and the B effectively becomes B times, because 1 mole of A is giving me B moles of B over here, so it becomes B times C alpha, where C is going to be initial concentration of A in this particular case over here. So it will be B times C alpha in this particular case here, if we have to write it in the terms of what exactly it's supposed to be. Now, if I was going to be having a slight change over here, if I had A moles of A giving me B moles of B here, if I want to write it as C into 1 minus alpha in this case also, we can, no problem. If I start off with C over here, I can say this is C into 1 minus alpha over here. This would have been 0 here. But ideally speaking, bring it off to 1 mole of A giving all of those guys. Effectively, in that case, what does this become? This becomes B by A into C alpha. That is the way to understand how much of B is going to be produced over here. So you can write the expression in this fashion here if you are having a different type of equilibrium given to you. Now, how you put it is going to be depending on what you define as alpha. If you are going to be defining alpha as the correct way it is meant to be defined, then yes, you can basically apply it in the fashion which I have shown you. If you define alpha slightly differently, then you will of course have everywhere, you will have a slight difference applicable over there. That is the way to understand the process over there. I am assuming you are clear with how to use alpha properly. Yes. Any doubts you have in alpha still left over? Or if you had any doubts, are they still left over?
No, sir.
Okay, alright. Now, when I'm assuming you are following consistently, yes. I'm not really going at a large speed because it's all basic shit only as of now. But things will start picking up in speed, or it'll be going on the same speed basically. So the next thing which you're going to be looking at is a standard typical model of question which you're going to be seeing in this chapter, which is going to be involving molecular mass of mixture at equilibrium or vapor density of mixture at equilibrium or density of mixture at equilibrium. Now, why am I mentioning each of these over here specifically? Because these are three ways in which a question can be given. Let me quickly show you a question over here and describe how it works out over here. So, let's say I'm going to be having PCl5. Okay, let's say the equilibrium is going to be PCl5 in equilibrium with PCl3 plus Cl2. So, if this is my equilibrium considered over here, in this here, they will tell us that at starting, we are going to be having something available. Okay, we are going to be having some reaction happening, some number of moles of PCl5 was there, or only pure PCl5 was there, that is dissociating. And as it dissociates over here, what is going to be happening is at equilibrium I am going to be now having a mixture. In that mixture they will ask us what is going to be the alpha for the mixture. They will ask us alpha for this. That is one way of looking at it. When they are asking us alpha, they might give us equilibrium constant Kp given. That is one model of question which can be asked over here. Effectively, there are three variables to look at over here. So, one of the variables is going to be in this question here. Alpha is one of the variables. The other variable is equilibrium constant. Now, this equilibrium constant can be given in many different ways. What do I mean? It can be given in many different ways. They can directly give me Kp. That is one way of giving my equilibrium constant. Another way of giving me equilibrium constant is by giving me alpha for the equilibrium or alpha for reaction. That is yet another way of giving me equilibrium constant. As I am saying here, alpha is also a way to represent equilibrium ultimately. It is a variable at equilibrium which you can calculate depending on what your variable at starting was. Obviously, starting variable will decide your alpha if you are going to be measuring alpha as a method of understanding equilibrium. Third, you are also going to be having other things which can be measured at equilibrium. One is going to be molecular mass at equilibrium. Another is of course going to be vapor density or density at equilibrium. These are all various measurements which scientists make at equilibrium. And each of these measurements is going to be something which of course has to be connected with the final equilibrium constant. They are all measured as the standard terminology in different places at different times. That is the goal here. So how do we connect all of these pieces together? So when you're going to be having all of these pieces together, you're going to be having some simple connections associated with it. In this particular case here, how to connect them in a simple manner. Let's say I started off with 1 mole of this bugger present. This is going to be 0 and 0 at the starting. We will have 1 minus alpha, alpha and alpha. This is going to be what is going to be at equilibrium over here. So the idea here is you are always going to be having some C moles at the starting. Now it is going to be some multiple of this. I do not care what multiple of this is actually going to be playing a game over here. Now if I am going to be having 1 minus alpha, alpha, alpha over here, how do I connect the equilibrium constant with the alpha over here? How do I connect anything with the alpha over here? What is the way to proceed over here? So easiest way is by using molecular mass at equilibrium. This molecular mass at equilibrium is going to be something which is very easily connectable to everything over here. So if I am considering molecular mass at equilibrium, this is nothing but molecular mass of the mixture present at equilibrium. Right. So that is very easy to calculate actually. So if I am considering PCl5 in equilibrium with PCl3, damn it. PCl3 plus Cl2, what is going to be happening over here is, let's say I started off with 1 mole of this bugger here. This was 0, this was 0. This was 1 minus alpha, alpha and alpha. Molecular mass at equilibrium can be easily calculated as, in this particular case here, total mass divided by total moles at equilibrium. This is a very straightforward and obvious assumption. This total mass though is something which, according to conservation of mass, should not change from the starting, right? This should be the same from start. Why should it be the same from the starting over here? Because of conservation of mass. Conservation of mass of course applies in this particular case here, which means this has to be the same from the starting. So if I'm going to be considering it this way over here, my total moles at equilibrium is going to be effectively easily calculatable over here. Total moles at equilibrium is easily calculatable as total moles over here, which of course works out as 1 minus alpha plus 2 alpha, which of course works out as 1 plus alpha. So total moles is 1 plus alpha, and at the same time my total mass is same from the starting. So if it is the same mass from the starting, that can be easily represented over here without any complications. So I'm going to be representing that molecular mass at equilibrium. This can effectively be written as molecular mass of this PCl5, because at starting I am only having PCl5 technically. So it's going to be molecular mass of PCl5 divided by 1 plus alpha in this particular case here. This is going to be the way to relate the molecular mass part over here. Of course, you can relate other things also once you have gotten molecular mass at equilibrium done. This is molecular mass at equilibrium. So once you have connected it with molecular mass at equilibrium and alpha here, you got a nice clean connection done. You can now connect the other terms. So for instance, I am going to be having ideal gases only. So I'm considering them as ideal gases only. What are we going to be having? We can effectively write Pm is equal to dRT. Right? This is going to be something which is allowed over there from the equilibrium, from the ideal gas equation point of view. So if I'm going to be having this over here, we can effectively say that pressure total at equilibrium. This is again going to be something which can be easily connected with various other things. So pressure total at equilibrium can be written as density of gas divided by molecular mass of gas into R into T. So in this particular case here, you're going to be having a nice expression connecting all of these, and of course you also know how Kp and Kx connect. So Kp is going to be equal to Kx into P total whole to the power of delta Ng, where delta Ng is of course going to be products minus reactants. So this is your connection over there, and of course in this particular case here, since you are taking 1 mole at the starting, these are not concentrations. For these, mole fractions are more easier to be played with over here. So usually in these kind of questions, if it is a very complicated top level question, they will give you mole fractions and they will give you connections, or they will give you some variables among these pieces over here. Your job will be to connect all of these pieces together and figure out what is going to be the unknown which you need to calculate to get your answer. Ultimately, the answer is also going to be connected to one of the variables there. So your job is to calculate some middle variable, then link it up with what you need to get for your answer over there to get your marks. So you'll have questions connecting these quite rigorously. How do you connect them over there? How do you interlink these bunch over here? Mole fraction in the same PCl5 case over here. Let me give you the expression there quickly. So we'll end up having it as 1 0 0 1 minus alpha alpha alpha, meaning we will have mole fraction of PCl5 working out as 1 minus alpha by 1 plus alpha, and mole fraction of PCl3 being equal to the same as mole fraction of Cl2, which of course works out as alpha by 1 plus alpha. So you'll have to sit and do the actual quadratic and solve this nonsense and get your shit done. This is going to be the theory generally associated up to here over here. Now, one other theoretical part which we need to discuss is what is going to be happening in case of heterogeneous equilibrium. When you're going to be considering heterogeneous equilibrium, what does this mean? This means the system pieces which are going to be at equilibrium are not necessarily in the same physical state or not necessarily connected in the same physical state here. How to proceed over here for these guys? Let's try to understand them a little bit over here. When it comes to solids which are crystalline, even if they are non-crystalline, they will have a density associated with them, but it is not going to be uniform. But if it's crystalline, you will have a uniform density. What does this uniform density mean? It means uniform packing of molecules. Molecules or atoms. What does this automatically lead to? This leads to same probability of finding a molecule, of finding a piece of solid. Which means if it is going to be same probability continuously, as long as a substance exists as a solid, you're going to be having it having the same density, or you can say its rate is constant, but depends on size and shape. If I have a solid in more powdered form, then it will react faster. Why does it depend on size and shape? It actually depends on surface area. It doesn't depend on other factors. It mainly ends up depending on the surface area exposed over there. So this is generally the case for solid over here. So as long as you're going to be considering from an equilibrium perspective, solid can be neglected. So from equilibrium perspective, concentration of solid is going to be a perfect constant, which is usually part of the equilibrium constant. If something is a constant over time, not necessarily only at the equilibrium, then we don't need to care about it. We can assume it is going to be something which is going to be the same even at equilibrium or at the starting. So generally, what do? Solids we can neglect from an equilibrium. Neglect. If in equilibrium with gases or solutions. Liquids also of course come into the same picture over here. Gases, liquids or solutions are present now. Ignore the solid. We don't need to care about that guy. Now, how about liquids? Liquids are also something which have constant density at given temperature. Because the volume of a liquid will change over time, which means its density will change over time. Volume of liquid will change in temperature, which means the density of the liquid will change in temperature also. So you're going to be having the liquids over here having constant density at a particular given temperature, so we don't need to worry about that part there. So these liquids also generally we can say if they are in equilibrium with solutions or gases, implies can be considered constant. So if these guys can be considered constant over here, basically can be ignored. What does ignored mean? It is part of equilibrium constant. Whatever K equilibrium which is calculated experimentally over there, this will automatically be a part of it. It doesn't mean we are taking it as 1. Alright, in certain places, in certain books, they mention it is taken as 1. It is not taken as 1. It is included as part of the equilibrium constant. Same goes for the solid over here. We are not taking the goddamn solid as 1. We neglect it, yes. But what does it mean? it means it is part of the equilibrium constant, it is a constant, so it is considered as included already. That is the idea there. If I have, say, gases and liquids, ignore liquids. Gases plus solids, ignore solids. Gases plus liquids plus solids, ignore solid and liquid. Solution, on the other hand, you have to consider. Solution plus liquid, ignore liquid. Solution plus solid, ignore your solid. Solution plus gas, take both. No ignoring. This is going to be the only case where avoid ignoring is basically going to be a better way. We will of course be seeing more of these cases in electrochemistry as and when necessary. So we'll go to the last part of this chapter now. Le Chatelier's principle. So what is the idea over here? There is going to be of course mathematics associated with this all in much greater detail. But Le Chatelier's principle from a very straightforward point of view, we'll discuss now. Le Chatelier's, I think we discussed this sometime recently with you, I have discussed this, is it, or have I not discussed this?
Did you you've referred to it several times?
So, shall I run through it anyway or what?
No problem, sir.
You are already clear with this?
Yes, sir.
Okay, I'll just discuss a few cases on this. I will give you the basic definition and I'll ask you a few cases questions basically. So let's say I'm going to be considering the standard equation for this, which is going to be ammonia preparation, Haber's process. This is going to be the standard thing which we all end up discussing wherever, because it's a very useful case, proper industrial case. So N2 plus 3H2 is going to be in equilibrium with 2NH3. Alright, so in this reaction here, this is going to be an exothermic reaction. So it is going to be releasing heat in the process over here. So let us start off with listing the conditions which are going to be good for this reaction. So what conditions will be good? Higher concentration of reactants, of course, and lower concentration of products. That is, I want to favor forward direction. So for forward direction, it is an industrial process, so we want to do more forward direction. We don't care about the equilibrium. Our job is to try to do more forward direction reaction to push the equilibrium into the forward direction to generate more ammonia. So this Haber's process is going to be production of ammonia. So I want maximum amount of forward direction. Implies what we are looking for is, implies want maximum forward direction. So we'll of course be increasing concentration of reactants as much as possible. We'll be decreasing concentration of products. How do we do this decreasing concentration of products? We effectively do a very simple trick over here. Dissolve full reaction mixture, or rather not dissolve really. Pass reaction mixture through water. So when I'm passing the reaction mixture through water over here, what happens is we are going to be having ammonia gas is highly soluble in water, so it dissolves in water. Whereas nitrogen and hydrogen are not that soluble. N2 and H2 very less in terms of solubility, do not dissolve much. So we can say it is approximately do not dissolving at all. So when it compares to ammonia, which dissolves, nitrogen and hydrogen are not dissolving realistically. So what does that mean? That means my product ammonia is continuously being removed out. So if I keep removing out a product over here, let us now quickly go for the basic statement of Le Chatelier's principle and try to understand what's the basic statement. Statement is, if a system at equilibrium is disturbed by surroundings. Anything which we do from outside is we are surroundings, is disturbed by surroundings, implies system will always do anything, or rather system will always do only things to correct it, will do only things to correct the change. Correct is basically not that good word over here. I'll use a better term over here. Instead of correct the change here, we can say correct or oppose the change. Oppose is a better word over here. Oppose anything surrounding has changed for the equilibrium of system. So effectively the idea here is we are going to be having system in equilibrium already. As surroundings, we are coming and poking it. We are doing something on it. When we are doing something on it, the system will do exactly opposite of whatever we have done. It will try to do exactly opposite of what we have done so that it can correct the equilibrium or bring it back to equilibrium in the cleanest manner possible. Again, there are hints about the words which I am using here, which hint about the direction of the reaction being related to delta G over here. Delta G, remember, that is where we talked about how a process can only do what is naturally spontaneous to it if you are not poking it. We'll come back to that all link in the next chapter in the conclusion of this topic over here when we are closing or winding off with equilibrium. Okay, so oppose anything a surrounding has changed for the equilibrium of system over here. Alright, so if the system at equilibrium is going to be disturbed by the surroundings, this is going to be what is referred to as Le Chatelier's principle. So if I am going to be pumping out the gas into water there, what is happening? I am going to be having more and more of ammonia, which is a product being removed over here. So if more and more of product is removed, more forward direction is going to be happening simultaneously. That is how we decrease the concentration of products over here and push this reaction in the forward direction. So how do we do it? We pass the reaction mixture through water. Okay. Next up, we are going to be having in this particular case here, heat is being released by the reaction over here, right? It's going to be an exothermic reaction. So if it's going to be an exothermic reaction over here, what is the idea over here? Forward direction is exothermic, backward direction is going to be endothermic. So let's try to understand how to proceed over here. What happens when you are going to be changing temperature here? So temperature is increased. So if you are increasing temperature from outside, what does increasing temperature from outside means? Heat is supplied. So you can think of it as heat being supplied in the process over here. So if we are supplying heat from the outside of the system as surroundings here, surroundings will try to, the system will try to consume the heat over there. So the system will push reaction. Reaction moves to endothermic direction if you are increasing heat. Endothermic direction in this particular case is backward direction for this particular case here. So backward direction happens more when you are going to be changing the temperature for this guy over here. In this equation, nitrogen, which is an exothermic in the forward direction over here. So because it is exothermic in forward direction, temperature increase implies more backward direction happens. This is going to be the case for ammonia production equation over here. Same way over here, when you're going to be having temperature decreasing, what does that mean? It means heat is removed from system. So system tries to produce more heat over here. So if the system is going to be trying to produce more heat in this process over here, what is the system really doing over here? System is now consuming heat or producing heat. It is going to be producing heat. So his system produces heat means moves to side which is exothermic. So if it is going to be moving towards the exothermic direction in this particular case here, how is that particularly going to be working out over here? So it is going to be moving in the exothermic direction, means for the ammonia production case here, it moves in forward direction. for Haber's process. There is a problem here. The problem is this: if I'm going to be considering N2 plus 3H2 is going to be giving me 2 ammonia. The actual temperature favoring scenario here is you're going to be having forward direction for Haber's processes if temperature is lowered. That means more forward direction at lower temperature only. But that is a problem. What is the problem over here? Because nitrogen is going to be having an N triple bond N, and the hydrogen is going to be H single bond H, which is the strongest sigma bond possible. So both of these bonds are very difficult to break. So what happens is we need a minimum temperature and heavy catalysis to actually reduce the temperature of the equilibrium as much as possible, because at lower temperature implies more or higher equilibrium constant. That is the idea over here. So if you want higher equilibrium constant, more forward direction, more product production, more profit, you need to have as low a temperature as possible. That is, for higher profit, what do we require? We require more products. And for more products, we require higher K equilibrium. And for higher K equilibrium, what do I require? I require lower temperature as low as possible, or temperature as low as possible. But what is the problem in this particular case here? This reaction is something which is going to be automatically having minimum required activation energy already being quite high. Why? Because N triple bond N is extremely difficult to break, H single bond H is extremely difficult to break here. Between N triple bond N and H single bond H, which is more difficult to break?
H single bond H.
Is it really? That's a goddamn triple bond, rah. Triple bonds are more difficult to break ultimately. There are 3 bonds to be broken in one thing, na? If I want one molecule of nitrogen reacting, I should have all 3 of those bonds breaking. Correct? Whereas H single bond H, yes, it is the strongest sigma bond, but that is sigma bond only. In N triple bond N, there is a sigma and 2 extra pi's. All 3 put together to break is much more difficult. Anyway, coming back to the reality over here, same thing happens in N and O reaction. Oxygen and nitrogen, they don't react with each other that easily. Hydrogen and oxygen react very, very easily. Look at the atmosphere. You're going to be having, and look at the earth, you're having a huge amount of water present, but you don't have that many nitrogen oxides. Why? Because hydrogen and oxygen can combine more easily compared to nitrogen and oxygen. That means in terms of bond breaking, N triple bond N is much more difficult to break compared to O double bond O, which in turn is more difficult to break compared to H single bond H. So when you're going to be having H single bond H over here, yes, there is the strongest sigma bond, but double bonds are stronger than single bonds always. Triple bonds are always stronger than double bonds. General cases, not always. I should never use always in chemistry. Almost in all cases, you can take it like that. So in this particular case here, the catalyst is going to work on specifically breaking N triple bond N. So catalyst is used to help break N triple bond N more easily. If I can break the N triple bond N more easily, then automatically I can decrease temperature as much as possible to minimum possible. So in this case, we use iron and manganese and chromium as catalysts sometimes. Those guys are basically going to be used in breaking what? It is used in breaking the N2 molecule. That is what we are helping in breaking over there. And the temperature at which we are going to be maintaining this guy is going to be at 500 degrees Celsius constantly. Because if I allow the temperature to increase, what does that mean? That means less of product is formed, less profit is basically made in the process. So I need to maintain temperature such that the bonds of the reactants can be broken, and I want to maintain it at as low as possible, so that I will have maximum K equilibrium, maximum product formation, maximum profit for me. Okay, so this is going to be the case with respect to temperature over here. Next up, N2 plus 3H2 is going to be in equilibrium with 2NH3. Let us now try to understand the effect of pressure over here. So if I'm going to be considering the reactants part over here, let's say I had like say 1 mole and 3 moles in the beginning, and finally let's say at some case it does get to full product production over there. How do you go push it to full product production? We keep removing product. Automatically more and more forward direction keeps happening. Full product is formed over there. If we do end up getting full product, what will be happening? This and this will be left over. This will be 2. So if I have 1 mole of this guy nitrogen over here, and each of these over here is present at standard temperature. At standard temperature, and I'm going to be having in this particular case here volume being equal to 22.4 liter container. Volume of container or volume of system, I'm going to have it as 22.4 liters. In that particular case here, I will have, if I had 1 mole of this 1 mole can be understood as the same as 1 atmosphere, and this 3 moles would have been understood the same way as 3 atmospheres, and simultaneously 2 moles over here can be understood as 2 atmospheres worth at the total pressure condition there. So we will end up having in this case here at start, this is going to be at start, we can say P total would have been 4 atmospheres when there are only reactants present, whereas at the ending we are going to be having P total being equal to 2 atmospheres in the process over here. So effectively what can we understand over here? We can understand and extrapolate over here that if more forward direction happens, implies P total is going to be decreasing, or we can say that pressure total for the system decreases over here. Why does it decrease? Because we are going to be having lesser number of gaseous moles in product, lesser gases in product, in stoichiometry of product. What does stoichiometry mean? We include this particular fellow over there, stoichiometry of product. That is the reason why you are going to be having in forward direction P total of system is decreasing over here. So if P total of system is decreasing, what does that mean? If from surroundings P external, or that if I am increasing P total over there, if P total is increasing, if we increase pressure from outside, if I increase pressure from outside, what will system do? System does opposite. So system will move more in the forward direction, and you will end up having more and more of forward direction happening. Why? Because you are going to be having lesser number of gaseous moles according to the stoichiometry in the forward direction over here. So for Haber's process over here, we will usually use high pressure. So what do? We take the reaction mixture, we keep it at very high pressure. Usually it is kept at a pressure of approximately 200 megapascals or 20 mega, at least like 20 into 10 power 6 pascal. I don't know how much it is going to be, at least 20 to 200, more than 20 for sure. So huge amount of pressure usually is used over here, and we compress the gases to a very high extent and then we pump it in. Of course, if I am going to be looking at pressure decreasing, it will go more in the backward direction. Why? Because in the backward direction you are going to be having more gases present. So more gases, more gaseous stoichiometric substances are there. So if you decrease the pressure, you will have more of backward direction. If you increase the pressure, you will have more of forward direction happening. Now lastly, on addition of inert gas, or actually we will discuss on addition of catalyst first. So when you are going to be having a catalyst basically added over here, what is the catalyst going to be doing? A catalyst is going to be offering a different path for the reaction to take. Alright, so if I am going to be considering a catalyst over here for a particular reaction, what is going to be happening in this particular case here? So reactant is like this, let's say product is over here. So if I have reactant and product in this fashion like this, so let's now understand what is Kf by Kb effectively. Kf by Kb is going to be my equilibrium constant, right? So Kf by Kb can be effectively written as, in this particular case here, Kf is rate constant of forward direction. So we can write it as A e to the power of minus Ea of forward direction by RT. This is going to be nothing but Arrhenius equation written over here. I can of course have it again divided by another A here. Technically it will be A of forward. I should have put this as Kb over here. I made a mistake here. By K of backward. So A of backward over here will have e to the power of minus Ea, in this case of backward direction by RT. This is effectively how we are going to be having the expression out over here. So the K equilibrium, if I'm going to be looking at it from a mathematics perspective over here, I can write it as some capital A. I don't care what that is, some AF by AB, I don't really care. Some constant A multiplied by e to the power of, in this case here, what we are going to be having is EA backward minus EA forward ends up becoming the case. So EA backward and EA forward, let's try to understand what they are over here. So EA forward is going to be this, where your reactant is going to be going and becoming the threshold over here. So this is going to be defined as EA forward. So let's define this level of energy also. This level of energy is called as threshold energy. So you're going to be having EA forward in this particular case working out as threshold energy minus reactance. Whereas if I'm going to be considering EA backward, what is that going to be effectively? That is going to be nothing but this thing directly over here. So this is going to be EA backward. So I'm going to be considering this as EA backward over here. I can write EA backward being equal to threshold energy in this case also minus products. So I'm going to be considering EA of backward minus forward. I can now write EA backward minus EA forward. How does that work out as? So EA backward minus EA forward, if I'm going to be considering, that is effectively going to be nothing but, well, reactants minus products. No, sorry. Products is in minus. Reactants minus products. Yeah, correct. Yeah. So it works out as reactants minus products in this particular case here. So if I'm going to be having EA backward minus EA forward considered, this is reactants minus products, which of course we have learnt in thermodynamics can be written as minus of delta H of reaction. It is not delta H forward, it is delta H of backward. So it is minus of delta H of reaction. So I can write this as e to the power of minus delta H by RT. This is basically what my K equilibrium works out as finally. So as you can see here, K equilibrium is related to temperature in this fashion over here. You can connect it with temperature here. You can also connect it with delta H over here. But the catalyst here, what is the catalyst doing over here? A catalyst offers a new path. Offers different path. So what does that different path basically tell us? Threshold energy changes, not delta H. Alright, delta H doesn't change, threshold energy changes. So what is going to be happening with the catalyst is you are going to be having a different path being offered. So in the different path, we will of course be having same reactant, same product, but threshold will change. This will be new threshold with catalyst, something like that. So the idea here is you're going to be having with catalyst, what is really going to be changing over here? So with catalyst, which is going to be a positive catalyst, helpful catalyst, we will have no change in equilibrium. So we'll have no change in equilibrium. When I say no change in equilibrium, what do I really mean here? I mean no change in equilibrium constant, no shift of equilibrium. If it is at equilibrium, if the system is at equilibrium, it will not shift. It will still remain at equilibrium over here. And simultaneously, no shift of equilibrium, no change in K equilibrium also. But one thing will change. The time taken to reach equilibrium, will change. And that will become faster or slower depending on if it's a positive catalyst or a negative catalyst. Positive catalyst, it will become faster. Negative catalyst, it will become slower. That's the idea here. Lastly, we're going to be looking at addition of inert gas over here. Inert gas does not react with anything in the reaction, so it doesn't work like a catalyst. So inert gas over here is not going to be influencing anything over here. Let's now try to understand how it influences the equilibrium on the other hand. So inert gas over here can be added at two conditions. Addition at constant volume. Meaning, I'm going to be having a rigid container. In that rigid container, I'm going to be pumping in extra inert gas here. So when I'm adding inert gas and it is added at constant volume here, we can effectively look at it like this. partial pressure of reactants and partial pressure of products will have no change. Why will they have no change? Because these guys are basically going to be, let's say I'm considering P of A, we can write as number of moles of A into RT by V. Temperature is not changing, number of moles is not changing, volume is not changing. So partial pressure is not changing. So if it is not changing, that means addition of inert gas at constant volume, no change or no shift to equilibrium. No shift of equilibrium. It is still at equilibrium, nothing changes. No shift of the equilibrium happens over here. So this is going to be effectively the same as this condition. No shift in equilibrium, no change in K equilibrium. Now, next up, if I am going to be considering addition of inert gas at constant pressure, this is going to be slightly different over here. So what does it mean, constant pressure over here? Constant pressure means we are going to be having P total or P external remaining the same. So P total and P external are basically the same thing. So P total for the system is going to be forcibly maintained the same. How do you maintain it the same? By making sure P external from outside is going to be remaining the same over here. So if I'm going to be having this as the scenario over here, what is going to be happening here? Let's consider the Haber's process itself. Haber's process was what? N2 plus 3H2 giving me 2NH3. So we had reactant side technically was 4 atmosphere at start, and product side over there, if we are going to be having this becoming 0, we'll have at ending over here 2 atmospheres at ending, which is going to be products at end. So what's happening? Technically speaking, forward direction is going to be what system will do. System does to decrease pressure, whereas backward direction system does to increase pressure. That is the idea here. So if I am going to be adding an inert gas at constant pressure, what is this realistically going to be doing? When we are adding an inert gas at constant pressure over here, what this realistically does is this. You're going to be having P total remaining the same. P total is constant. But you're adding an inert gas implies P of inert gas increases from 0 upwards. Correct. So if it's going to be increasing from 0 over here, what is going to be happening to all the other fellows over there? Pressure of reactants and pressure of products. Or instead of writing as pressure of reactants and pressure of products, we can say pressure of and or both are correct there, and or plus, you can take it as both are correct over here. Pressure of reactants and pressure of products both decrease. If it is basically decreasing, equilibrium, what will the equilibrium see this as? Equilibrium sees this like decrease in pressure. Let me not put that bottom line there. So equilibrium sees this as decrease in pressure. Decrease in pressure. Because equilibrium sees this as decrease in pressure, it will do what it can to increase pressure. System does what it can to increase the pressure back again. That is basically what it will be doing here. So if you pump in an inert gas over here, what will the inert gas do over here? That inert gas will push the reaction a little bit more in the backward direction in this Haber's process over here. So no inert gas, you will have nitrogen, hydrogen and mixed together, and you will end up having a huge amount of catalyst over here, which is going to be iron, chromium, molybdenum, whatever is there in your NCERT textbook in nitrogen chapter. And you will have, constant temperature of 500 degrees Celsius being maintained in the process over here. So more or less this is basically a blast through of chemical equilibrium only, and I have another class in a while and you also have to get out at 11 is what you told. So we'll close the class now. Tomorrow same time works for you? Morning?
Sure, sir.
Morning as of now is fine?
1 second, sir.
Confirm of this.
Yes, sir. Tomorrow works. Sir.
Tomorrow is perfectly fine. No problem for the morning there.
Yeah.
Tomorrow is Pongal though,
Yeah.
na?
Um, I think yes. I don't know, sir.
Okay, alright. If morning is fine, you have confirmed with your parents.
Yes, sir.
Okay, alright then. ठीक है हाँ. Alright then. I will see you tomorrow. Tomorrow I'll be mostly doing a blast through of ionic in a similar manner. Um, alright. Any pieces of chemical equilibrium which you still have left over as doubts? Theory wise, you said chemical equilibrium theory. You wanted to run through it once. Are you properly cleared out with chemical equilibrium theory here?
Yes, sir.
You understand there are parts which I have purposely ignored. I've given you hints of it, but I've ignored over here. Basically, connecting G and delta G with equilibrium over here. I will touch upon them a little bit once I am done with ionic equilibrium also. Because ultimately, ionic equilibrium is where all of these connect with electrochemistry, and that's where all of these equilibrium pieces connect with each other as well. So, I'll see you tomorrow in the morning for a blast through of ionic equilibrium. I'll see if I can post questions on whichever topics we have discussed so far. The what to say standard model questions which are you. I already discussed most of the stuff which is necessary for questions, but there are going to be some standard models in JE mains and JE advanced. If there are any interesting models, I'll post them online. I'll share the link with you, and you can go and have a look at it when you have time. I'm assuming you have internet connection properly available, na? No problems, na?
Um, I think so, sir. Yes.
Okay, all right, huh? Take care then. Bye bye. Have a nice day.
Thank you, sir.